In this video, we continue our description of key thermodynamic variables by introducing the concept of heat. Right, we have said that energy can be transferred as only two ways. It's either work or heat. In a prior video, we have seen how to calculate energy transfer as work in a gas expansion. Right now, what we're going to do is then turn our attention to energy transfer as heat, and then begin to see if we can calculate how much that energy transfer as heat is for a common example. Now, calculating the energy transferred as heat can be quite complicated, and in this video we're simply going to constrain ourselves to a very simple example which requires a change in temperature in an object. Okay, so the first thing that we're going to do here is to use the nomenclature that is normally used for heat, and heat actually appears as the letter Q, okay, and that is in distinction with work, which has the letter W. Right, let's talk about the sign convention as well before we get started. Again, remember that heat and work are forms of energy transfer. Right, so the way to determine the sign of heat and work is to simply look at the energy in what respects to the system. Right, so if the system is gaining energy, then as either work or heat, then that work or that heat, that energy transfer that is making the system's energy go up, will be positive. However, if the energy of the system is dropping because energy is being transferred out to the surroundings as either work or heat, then those work or heat will be negative. Okay, so that's where we start. All right, so now that we have defined the letter that we're going to be using for heat and then the sign convention for that energy transfer, then we can begin to see how we would calculate the energy transfer as heat in a very simple example, which is when there's a change in temperature in an object. Okay, so suppose that we have here gas inside a cylinder. Okay, so this is where your gas is, and then what we're going to do is deliver some amount of energy as heat to this gas, right? So this might be maybe with a Bunsen burner, right? Here we have a burner that is going to elevate the temperature of that gas. And then the question is, well, how do we calculate the amount of heat transfer to that gas when you have this Bunsen burner here heating the gas? All right, so there's a property of that gas that is key in determining how much energy is transferred as heat, and then the change in temperature. Okay? As it turns out, the change in temperature is proportional to the heat delivered. Okay, but of course, there has to be something that depends on the gas, right? So it's not the same thing to try to elevate the temperature of liquid of water gas or neon or argon or methane, and that should be also different with respect to whether that is a gas or a liquid, right? It's not the same thing to try to elevate the temperature of a liquid than a gas, right? So that property that controls exactly what the sensitivity of the system to a change in temperature is according to some energy delivered as heat is what we call the heat capacity, and we're going to be calling this C. All right, so again, notice that if a substance has a very high heat capacity, then if you deliver some amount of energy, the change in temperature will be very minor. However, for a substance that has a very low heat capacity, then delivering the same amount of energy will give rise to a large temperature change. Okay, so that tells you how that heat capacity, which is specific to its substance, controls the change in temperature that substance experiences when some energy is delivered as heat. Well, so this equation then allows us to actually then calculate what the heat transfer to this gas would be. The only thing that we would need to do is just figure out what the change in temperature is, but that should be pretty straightforward. Right? If you know the heat capacity of the substance that you're changing the temperature, and you can measure the change in temperature, which you can do with a thermometer, then you can determine how much energy has been transferred as heat. Okay. Right, so then let's figure out here what the units of this heat capacity are. Okay, notice that heat is a type of energy transfer and will have units of joule. And then in the SI system, temperature has units of Kelvin, right? So then that means that the heat capacity in general is going to have units of joules per Kelvin. Okay? Now, This heat capacity comes in very many flavors. Okay, notice that the heat capacity in this particular case, what we have right here, depends on how much gas you have, right? You can think about doubling the size of this experiment, and then obviously you would need to transfer twice the amount of energy in order to produce the same change in temperature. Okay, so what that tells you is that, well, the heat capacity as defined in that expression depends on the amount of sample. And that's something that you want to avoid, right? You would like to have something that does not depend on the amount of sample. And for this purpose, we define a couple of heat capacities that, again, are irrespective of the amount of sample that you have, right? You can have C sub S, which is called the specific heat capacity. And this has a definition of the heat capacity divided over the mass of the sample that you're considering, right? So the units of this will be joules per Kelvin, and then per unit of mass, which is generally going to be grams. Okay, so that is one way to get around this dependence of the heat capacity on the size of the system. Another way, which is going to be even more common, is to define something that we call the molar heat capacity, right? So that will be the heat capacity per mole of substance, right? So the definition would be that's the heat capacity for each 1 mole of the substance that you're interested in, and then the units of this are going to be joules per Kelvin per mole. This is certainly going to be the most common heat capacity that we're going to be using in problems. It will be a molar heat capacity. Right, but heat capacities can be even more complicated than this, right? So in this example, we actually have moved from a heat capacity that depends on the system size to a heat capacity that does not depend on the system size, and that actually is very useful. But it also turns out that the heat capacity depends on the conditions of the experiment. Okay, so for example, imagine that you have here that same gas, okay, and we're going to try to deliver the same amount of energy as heat in 2 different cases. Okay, so in the first case, which we have right here, okay, we're going to block this, or we're going to lock this piston into place, right? So that piston will not be able to go up once the temperature starts to increase, and that is what we call constant volume type of experiment, right? That piston can move, that means that the gas always has the same volume. And then another experiment that we can do is exactly the same one, right? So here you have your Bunsen burner. Okay, we're going to be elevating the temperature of that gas. But then in this case, what we're going to do is just let the system change pressure as it wishes, so that the pressure stays constant with respect to the atmospheric pressure, right? So what will happen, the expectation would be that you expect that piston to be pushed out by the system, right? So this is what we call constant volume. And this is what we call constant pressure. Now, it's very obvious to recognize then that in this case, the system is actually doing some work, right? Because that piston is being pushed out from the systems into the surroundings. Then some of the energy that the system is gaining when you deliver energy as heat is actually being lost as work. And what that means is that, well, you're going to have to deliver much more energy in this case than in that case if you want to change the temperature by the same amount. Okay, so notice what that ultimately means is that the heat capacity, if you're working at constant pressure or at constant volume, will actually be different. And it is always the case that the heat capacity at constant pressure has to be higher than the heat capacity at constant volume. And the explanation is again this one. Right? When you're working at constant pressure, you're allowing for some of that energy to be lost as work. Okay, and what that means is that you need to supply more energy. There's an effective larger heat capacity in order to be able to change the temperature by the same amount than if you're working under constant volume conditions. Okay, so then these more heat capacities are going to come generally in 2 flavors. You're going to have your molar heat capacity at constant volume, C sub Vm, and your molar heat capacity at constant pressure, C sub Pm. Right, so just to show you a value for a heat capacity for a common substance, the heat capacity, the molar heat capacity at constant pressure for liquid water at around room temperature is about 75.29. joules per mole Kelvin. Alright, so now that we have introduced how to calculate the energy transfer as heat for a substance when its temperature changes, and the meaning of the heat capacity, we're actually going to run a problem to try to illustrate these concepts. Okay, so the problem is going to be not a gas, but it's going to be liquid water, okay, which we're going to have in a flask. Alright, so this is our flask with liquid water, and this is the level of liquid water, that is H2O liquid. And we know that the heat capacity at constant pressure, the molar heat capacity at constant pressure is 75.29 joules. Right, so the question is, well, suppose that we have here 20 mils of water, and the density, so the volume is the density of that water at around room temperature is about 1.00 grams per milliliter. And the question would be, please calculate how much energy as heat needs to be transferred to this liquid water to elevate its temperature from 10 Celsius to 20 degrees Celsius. Okay, so that's what we want to do. The change in temperature will be, or the initial temperature will be 10 Celsius, and the final temperature will be 20 Celsius. Right, so determine how much energy as heat needs to be transferred to elicit that change in temperature. All right, so then our root expression is going to be this one, right? That's how we calculate heat whenever the only thing that is happening to the system is simply a change in temperature. We actually already have what that delta T is. This is going to be the difference in temperature between 20 and 10. We just have to figure out how to come up with this heat capacity. Okay, notice that we don't have the heat capacity for the sample, we simply have the molar heat capacity. Okay, so there has to be a way to transform the molar heat capacity, which is provided by the problem, that's 75.29 joules per mole Kelvin, into the heat capacity that you have in this expression. And the way to do it is actually right here. Notice that the product of the molar heat capacity multiplied by the number of moles will be equal to the heat capacity that you need in that expression. Okay, so this expression then turns into the following. Q is going to be equal to the number of moles times the molar heat capacity times the change in temperature. Okay, that is how you relate the heat capacity of the sample to the molar heat capacity, which is tabulated, given in tables. Now we're working under constant pressure conditions. This water is not under constant volume, so then we actually can say that that's simply constant pressure conditions, and then we have the number already. All right, so we have this number, we have the change in temperature. The only thing that we need to calculate then is the number of moles of water that we have. And that's just a pretty simple calculation from the volume and the density. Okay, how do we do this? Well, notice that if you have the volume 20 times 0 mils multiplied by the density, which is 1 gram for every mil, this calculation is going to change the volume into mass. And then to go from mass to moles, you simply have to divide over the molar mass. Right? We know that for every water molecule, there is 18.02 grams. Okay, that is the molar mass of water. So that changes your grams into moles. Okay, that calculation that goes from volume to mass to moles, okay, is what we need for this particular problem. And this number happens to be 1.11 mole. Okay, so then we're ready to solve here. The Q will be 1.11 mole of water multiplied by the heat capacity for each mole of water at constant pressure, 75.29 joules per mole Kelvin. And then here you will have to multiply this by the difference in temperature. Now my recommendation here is to always work in Kelvin. In this case you're taking the difference, which is not going to matter to the delta T. Right? Notice that when you transform that into Kelvin, that will be 283 Kelvin. And this is going to be 293 Kelvin, okay, with that level of precision. Right, so the change in temperature is going to be the same in Celsius and in Kelvin. However, in some other equations that we will see, you'll have to take the ratio of the temperatures, not the difference. And then in that particular case, doing the calculation in degrees Celsius will be incorrect. Okay, so just to get a good training and run smoothly with these temperatures, I always recommend you to do this calculation in Kelvin. Right, so that will be the change in temperature, that will be 293 Kelvin minus 283 Kelvin. And we just have to verify here that the units cancel out. Okay, notice that this mole cancels with that mole, that Kelvin cancels with this Kelvin, and the only thing left over will be your joules. Okay, so that is exactly what you need to have, and when you operate, you need that 836 joules of energy are needed in order to elevate the temperature of 20 milliliters of water under constant pressure conditions from 10 Celsius to 20 Celsius. Right, so in this video we have introduced the concept of heat, we have talked about sign convention, and then we have discussed one of the easiest ways to determine energy transfer as heat, and that is what happens when the only process going on is a change in temperature of a substance of known heat capacity.